In this video, we're going to discuss the enthalpy of phase changes and how to calculate them. For this, we need to think about what happens to a material as we heat it up. So let's put some energy in and look at the temperature. We're going to start at minus 15 degrees Celsius. At this point, we are ice. We're going to look at water. For a little while, as we add energy, our temperature is going to go up. So we'll add some energy and our temperature will increase. So you put an ice cube on a pot on your stove and you turn on your stove. And for a while, we'll get this line until we hit the freezing point, or in this case, the melting point, which at standard pressure is going to be 0 degrees Celsius for water. When you hit a phase change, a temperature where you'll swap from one phase to another, for the next little while, we don't see a temperature increase. We continue to add energy, but we don't see an increase in the temperature. Instead, what's happening is we're changing some of the molecules from solid into liquid. So I'll have a large block of solid. As we start to heat it up, they'll all vibrate a little bit more and vibrate, and then right at 0, more energy pops this out and gets it rolling. It breaks it out of its position and gets it going. The next little bit of energy pops this one out and it starts rolling over as well. Next one pops the next one out, and bit by bit, that energy starts getting everything free-flowing. Eventually, all of it is rolling around. At this point, any more energy, well, we're all liquid at that point. So while we melted, we went from 100% ice and 0% liquid to eventually being 100% liquid and 0% ice. Anywhere along the middle, we still had a mixture of the two. If you've ever watched an ice cube melt, it doesn't pop like a water balloon, though that might be kind of neat. It just drop by drop, some liquid weeps off of it until the ice cube is melted. From this point on, adding more energy is going to raise our temp. We are liquid. This just gets the liquid moving faster. They bounce all over, get going even quicker, until eventually this is going to reach another phase change at 100 degrees Celsius. Again, while we go through that phase change, we will not see a temperature increase. This is when we're going to boil. What happens here is these molecules getting faster and faster eventually can just break off. They can drift away. And this becomes a gas. The molecules all spread out as they break free of each other. And eventually what you have is a gas. And at that point, any more energy would just heat up our gas. This is what it's going to look like as we actually attempt to add energy to our ice cube, from beginning all the way up to gas vapor. Unfortunately, because our line changes at different times, we need different calculations for each section. Here's one section, here's a second section, here's a third section, here's a fourth section, and if we really wanted it, there's a fifth. Each of these requires its own calculation to determine just how much energy is going in to make that change. I cannot start at minus 15 degrees Celsius ice and calculate directly the amount of energy added to get up to, say, 120 degrees Celsius gas. I'm going to have to do each of these parts individually. Also, how do we do that? Probably in previous courses, you may have seen heat capacity. Within a phase, so ice to ice, liquid to liquid, or gas to gas, this was calculated as the change in enthalpy required was equal to the constant of heat capacity, a C or an S value, times the change in temp. Every material had some amount of energy to go up 1 degree, depending on the amount of material, which requires us, if we have more than a single gram, to also include the mass. And how many temperature degrees we want to go up, this would determine how much energy. The S value for liquid water is 4.184 joules per gram per degree. And this can be Celsius or Kelvin, as long as you're using that temperature in your delta T. Either is acceptable in our S value. 1 degree Celsius increase is a 1 Kelvin increase. We're only looking for the difference, not the absolute temperatures. Well, this is also true if we're going from solid to solid. So an S value for solid H2O, or if we're going gas to gas, an S value for gas phase H2O. This is 2.05 joules per gram per degree, and the gas phase is 2.08 joules per gram per degree. Often this is rewritten as Q equals ms delta T or mc delta T, depending on your book source. However, if we want to go through a phase, so this covers our purple section, our blue section, and the multicolored at the end. If I want to go through the green section, the melting, or the violet section, the boil, for this, I need a phase change. For this, our calculation is that the energy is equal to the mass, whatever size our sample is, times the enthalpy of either fusion, if we are melting, or the mass times the delta H of the vaporization if we are boiling. For water, the enthalpy required to melt for fusion is 6.02 kilojoules per mole. When the solids reached the point where they were vibrating enough that more energy started popping them free, it took 6.02 kilojoules per mole of water molecules to make them all pop free and start flowing over each other. The delta H of vaporization, on the other hand, is 40.7 kilojoules per mole. Breaking the molecules completely free of each other requires a great deal more energy than just getting them moving around each other. Our delta H of vaporizations are always greater than our delta H of fusions as a result. Well, combining these, we can take a sample all the way from ice up to gaseous water. We'll do that in our next video to show how these work.